The last and sort of almost standalone thing you need to know about is cellulose. So cellulose is also a polysaccharide. It's also a polysaccharide of glucose. So it's formed from 1,4 glycosidic bonds. And some of you may be thinking, but I thought amylose and amylopectin and glycogen had 1,4 glycosidic bonds. And you'd be right to say that, but cellulose is made from beta glucose. So if we look here, we have our glucose, and we've got 6, 5, 4, 3, 2, 1. And we look at our carbon 1, and we look for our H group, which would be here because the OH is up. That is below. So what we have here is lots and lots of lots and lots of beta glucose, and we need to make a polymer from it. And sometimes, occasionally, you will have sort of diagrams showing you form a glycosidic bond like this. So we take out that OH, we take out that OH, and you get a glycosidic bond forming here, and they go like beta 1,4 glycosidic. But that's actually incorrect, and that's not how glycosidic bonds in beta glucose form. Actually, what ends up happening is you flip this molecule, and actually this is where OneNote is really helpful, because if I go flip and then flip again, you get alternating. You sort of get one right way up, one upside down. And again, look for the prong to orientate yourself. So actually this is 6, which means this is 5, and this is 4. And this is actually where our 1,4 glycosidic bond comes from. So you get one coming down here, and then you get another one coming down here. And actually you end up sort of with this alternating fashion. And what's interesting about this is it forms this polymer is a long straight chain. It's not that lovely coiling pattern that we saw. And this is cellulose, and this is what sort of you get these bands, and they're almost like a rope that can wrap around a cell and form its cell wall. So these nice big ropes. But there's another subtlety and nichety to it that's lovely. So this is what you'll sometimes see it drawn as, where actually rightly one of the molecules has been flipped over. And what's lovely about it is this. So if we take this molecule, and if I sort of highlight, so that's one chain, that's another chain, and that's another chain. We need cellulose being exceptionally strong, because it needs to be able to withstand turgidity or turgor pressure, which is that old sort of idea of a cell membrane. If a cell swells with water, the cell membrane is going to push on the cell wall. And it can actually form quite a high pressure, and you need something that's strong to deal with that. And the idea is these chains or fibrils, as they're known, can actually come together via hydrogen bonding. And some of you may have noticed that in this chain and this chain, you've got OH next to each other. And as we've seen from water and everything else, these OHs all sort of form hydrogen bonds with each other. And you end up forming these big old fibers of cellulose, which are extremely strong, because you've basically got rope. You've just got straight chains of covalently bonded things together, with hydrogen bonds strapping all of those fibrils together, which gives it its strength and gives it its very, very high tensile strength to deal with turgidity. Equally, the fact that all those OH groups are sort of hidden away, bonding to one another, hopefully you will realise that water therefore can't form hydrogen bonds with one another with it as well, so it also makes it insoluble.